Okay, in this section on mathematical induction, we're proving statements using a methodology. And we're going to go over some basic stuff. It's in your book if you want to look on page 859. And basically what we want to show is that this statement here is true for any number, any positive integer, all natural numbers, for any natural numbers that it works. So first of all, let's look at this. First of all, on this one, we have, these are odd natural numbers. This is basically the formula for odd natural numbers. So what we want to do is we want to check, and we're going to check for n equal 1. We plug in 1, we're going to look at 2 times 1 minus 1, that equals 1. So we're looking at this, and we're going to also plug it in here, 1 squared. So does 1 equal 1, and that checks. And it's supposed to also equal your first term. Now for n equal 2, that means that's your first two terms, because this is ace of 2. So we're going to plug in 2 times 2 minus 1, and that equals, well, what we're going to do here is, basically, start over again. Basically, we want to show that for n equal 2, the sum of the first two is 1 plus 3. And 1 plus 3 equals 4. Now for n equal 2, I'm also going to plug it into this formula. So you have 2 squared, and that equals 4. So that checks. Now for n equal 3, basically we're checking all 3. So when you check all 3, we get 1 plus 3 plus 5, that equals 9. And we're also going to plug in 3 in this formula, so 3 squared equals 9. And if you want to check some more, you could keep going on. N equal 4. So you're going to get the first 4 terms, which is 1 plus 3 plus 5 plus 7, which equals 16, which also equals 4 squared, which equals 16. So that would be plus, that would be the 7 would go there. Okay, so basically this is what they're talking about when they're proving it holds for all natural numbers. And usually we talk about positives, so we talk about, but it's for all natural numbers. Okay, now, when we're doing principle of mathematical induction, you have to follow the form. It's not just a matter of, plug it in. You have to do all the steps, and the steps can be a little cumbersome, but that's what the proof is about, is knowing that you know how to do the steps. So the first one we're going to do is number 1. And number 1 is on page 862, and we have 2 plus 4 plus 6 plus ... plus 2n. Of course, this is the formula for all even integers. And they say that this equals n times n minus 1, n times n minus plus 1, All right? Now, the first thing you have to do is check for conditions. We have condition 1. So in condition 1, we have to show, does it work for n equals 1? Okay, so if we plug in 1, that's the first term. We should get 2, because your first term is 2. Now plug in 1 here. 1 times 1 plus 1, that equals 1 times 2, which is 2. So, yes, that condition holds. So condition 1 holds. All right? Now, for condition 2, we're going to see if it works for all k, and you have to write this down. So you're going to have to repeat and write and a bunch of stuff. So we're just going to write the same formula down. Plus, I notice that students that don't do this tend to mess up in here. So all we're doing is replacing the n's with k's. And now we're going to check, does it work for the next term? So the next term would have been what? N equal 2. But we're not going to keep checking each number like that. We're just going to use the proof. So we want to check for if it holds for k plus 1, the next term. Okay, so the next term to this would be 2 times k plus 1. All right? So basically, you're going to write this down. Copy it down again. Let's copy it down in a different color. 2 plus 4 plus 6 plus dot 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 plus 2k plus 2k plus 2. I'm just distributing. So basically everywhere there's a k, I just substituted k plus 1. Now, if I want to, I can go ahead and put in k plus 1 here. So here, on this side, I can put k plus 1. So for this k, I'm going to put k plus 1. And for this k, I'm going to put k plus 1. So that's going to be k plus 2. So basically, I'm just adding 1 to each of these terms. Okay? Now, the next step. The next step is we know what this equals. This equals k times what? K plus 1. So we're going to write that down. K times k plus 1. Then we're going to add this plus 2k plus 2. And we're going to check if that equals our k plus 1 times k plus 2. And you can FOIL that out if you want, but we don't really need to. So what I'm going to do here is clean this side up. So we have k squared plus k plus 2k plus 2. Excuse me. So that equals k squared plus 3k plus 2. I'm going to factor and we get k plus 1 times k plus 2. And yes, indeed, it equals k plus 1 times k plus 2. So, bottom line, the statement is true because conditions 1 and 2 hold. So this is true. And by the way, all these will be true. Don't ever write on the test that's not true, unless I have a typo or something. Okay? So let's go do 3 now. So 3 we have 3 plus 4 plus 5 plus dot 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 n plus 2 equals 1/2 n plus n times n plus 5. Now, what I'm going to do is I'm going to check for condition 1. I'll just go C1. And I'm going to see if it's true for n equals 1. All of a sudden it didn't want to work. Okay, so n equal 1. All right. So basically my first term is 3. And I'm going to plug in 1 over here. So I'm going to get 1/2 times 1, which is just 1/2. And 1 plus 5 is 6. And that equals 3. So this equals 3. So these two numbers match, so condition 1 holds. Since it does, we're going to check for further conditions. So we're going to check condition 2, and you have to follow this step. The first step is substitute n for k. So we're going to just copy this down. Should have been a plus there. Plus k plus 2. So we're checking for all natural numbers, not just one. All right. Now we're going to check for k plus 1. All right. So basically I'm going to write this down again. 3 plus 4 plus 5 plus dot 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 plus k plus 2. And the next one's going to be k plus 3. All right. Because this is, you just substitute k plus 1 here. And k plus 1, and then 1 plus 2 is going to give you 3. Now, over here we're going to do the same thing. So we're going to get 1/2 times k plus 1. And this part's going to be k plus 1 plus 5 is going to be k plus 6. Okay? All right. Now, we know that this right here equals this, because it's on this first line. So that equals 1/2 k times k plus 5. And now I'm going to add the plus k plus 3. All right. All right, now what I'm going to do here, and this is an algebra trick, instead of distributing this 1/2, what I'm going to do is write this 1/2 out here, and this is fine here. But I'm going to multiply this by 2. That way I can set it inside and work this all together. Now when I do that, if I distributed this, I would get this back here, and the 1/2 times 2 would go away. So when you do that, you're going to get 1/2, and I'm going to clean this up, k squared plus 5k plus 2k plus 8. Clean that up, and you're going to get k squared plus 7k plus 8 to the 1/2. And when you factor this, you're going to get k, what did I do here? This is 6, sorry. See, at least I don't have to start the video over, so this is really 6, right? So this is 6, because I can't factor that. All right, 6. These come out really nice, so it's going to be k plus 1 times k plus 6. All right? And it indeed matches this, so that equals 1/2 k plus 1 times k plus 6. Okay, the trick happened right in here. So it's little algebra tricks on this. You're going to have to know how to do that. All right? So let's do number 7. So number 7 is 1 plus 2 plus 2 squared plus dot 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 plus 2 to the n minus 1 equals 2 to the n and then minus 1. Okay, so we're going to check for condition 1, and we're going to check for 1. So I'm going to plug in 1, and we should get 1. So 2 to the first power minus 1 equals 1. So n equals 1. It doesn't like my equals. That's true. Now we have to check for condition 2. That means we're checking for k plus 1. Now the first thing we're going to do is just write this whole thing out like we did before. Instead of n, we're putting what? K. Okay. Now we're going to check for k plus 1. So we're going to copy him down exactly the way we see it. It's 2k minus 1. Then we're going to add k plus 1. So if I substitute this k for k plus 1, that's going to just leave me with 2k. Okay? Now, so this is the next term. And then here we're going to have 2k plus 1 minus 1. Okay, now we already know what this equals. This equals 2k minus 1 plus 2k. Okay? And when we do this one, we're going to just write it out as this side right here can be written as 2 times 2k minus 1. We'll talk about that in class a little bit. So this side we're going to have, I don't like how they did this. Okay, so basically what they're doing is they're going to write 2k minus 1 plus 2k. So basically when you add these two, this is going to be 2k plus 1 minus 1. Okay? Alright, so these two match up, and the condition holds, so condition 2 holds and condition 1 holds. So this is true. And again, they'll always be true. Okay? Alright. Okay, the last one we're going to do is number 9. Alright, on number 9, we have 1 plus 4 plus 4 squared plus dot 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 plus 4n minus 1 equals 1/3 to the 4n minus 1 minus 1. Make sure you write those right, because I didn't write it right on the other slide. So basically we're going to check for n equals 1. So when you know n equals 1, we have the 1 here. So we're going to have 1/3 to the 4 minus 1, which is 1/3 times 3, which equals 1. Now, that condition 1 holds for n equals 1, because 1 equals 1. Now, for condition 2, we're going to substitute everything for k, so we have 1 plus 4 squared plus dot 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 plus 4, change it to k, little k minus 1 equals 1/3 to the 4k minus 1. Alright, now we're going to check for k plus 1. So you write this whole thing down again, and we're going to get 1 plus 4 squared plus dot 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 plus 4 to the k plus 1. Well, no, we have to write this down. Don't make the mistake I did. So 4 minus 1 plus 4k equals 1/3 to the 4k plus 1 minus 1. Alright, now we know this whole thing equals 1/3 to the 4k minus 1, and then we have plus 4k, little k. Alright, now clean this up, and what I'm going to do, since I have this 1/3 here, and I know it's out here, I want this side to look like that side. I'm basically going to take this whole thing and multiply this by 3. Now, after this, how many 4k's do I have? I have 1 here, and I have 3 here. So basically, I have 4 of these. 4 times 4k minus 1. So all I did was add this 3, and this was like times 1 of those. Alright? And then you should know that, and we already should have talked about this in class, so this right here can be written as 4 times k plus 1, and then you have your minus 1. So right here, these two are equivalent. All right, and that equals that. So basically, that's principal mathematical induction. I will do the evens for you as well, but you only need to know how to do 1 through 10.